in the given time constraint, it's really not possible for me to do a better job. However, if you do want to learn more from a more formal mathematical point of view, I think there's a very good book. And of course, I don't want to recommend a whole book to you. I'll recommend a chapter. So there's a very nice book on differential geometry and stuff like that by, I don't know how to pronounce this, Göckler or Göckler? I think so. So chapter 8 I recommend that you look at that. The other issue that came up is that somebody said that my statement of Wigner's theorem was not precise enough. And again, that's true. And so I don't intentionally make statements which are technically wrong. But if I do, please, point them out to me. And so if you want, I think I mentioned this again, if you want to look at a more detailed proof of Wigner's theorem, look into Weinberg. Volume 1, and I think it's chapter 3. So again, I'm not recommending a whole book, but that if you're interested in certain thing, you just go in. And that's kind of the spirit of this whole course. I mean, it's group theory is kind of an advanced subject, especially at the level that in physics we don't need a lot of rigor, but what we do need is some smattering of ideas, okay? Such as what is a representation, what is a group manifold, and things like that. So my aim here is to just give you a kind of a smattering of these ideas, and really geared towards those people who haven't kind of seen a lot of it, so that you have some point of departure, okay? And I'll also put up these references in the wiki, so if you want to explore them more, you're welcome to do that. And also, like, after the course is done, I mean, right now I'm extremely busy, as you can see, like just doing this course. After the course is done, if you want to, say, discuss some of these in more detail, say, oh, I want to get this point, you can always come and talk to me, and I will help you. I will try to help you, to my utmost. Okay. I'm not running away after the course. That's what I'm saying. All right. So some of the other questions that came up that people asked, I will address them during the lecture when the context arises. Okay. Okay. Anything else? All right. So let's start then. So last time we finished with the statement that the generators of say SON were antisymmetric matrices. And we label them with two labels in a clever way, where there was exactly n times n minus 1 by 2 linearly independent matrices. Now suppose, okay, so there are two cases. Suppose that n of SON is an even integer. Okay, so L is some integer, so n is then we can define L linearly independent matrices or generators which are of the form H1 and everything else is 0. And H2, well, I notice you're also wearing a tie. Nice. You should have told me. I could have totally worn a tie. So until you get HL, where everything is 0 except the last 2 by 2 block. And okay. Now it should be clear that all these matrices commute with each other, right? So okay, for all I. And I gave you the generators for the other elements as well, right? Last time, because okay, well, I said that the general formula is it's an antisymmetric, right? So I gave you a general formula for all the matrices last time, right? So this observation leads us to an important idea, and the idea is it's called the Cartan subalgebra. So the Cartan subalgebra is the maximal set of mutually commuting elements of a Lie algebra is known as the Cartan subalgebra. And for SO2L, you can convince yourself this is the maximal set. And the way to see it is to see that each of these generators generate rotation in disjoint planes. Okay? So HI generate, okay, the set HI generate rotations in planes which do not share an axis. And therefore, they would be commuting rotations, right? Now, if two of these matrices, if two matrices shared an axis in the rotation it generated, they would not be commuting. So all the other matrices in the Lie algebra of SON, like none of the other matrices in the Lie algebra of SON will commute with these guys. right? Because they will necessarily, involve a rotation which involves one of the directions that's covered here. Okay. Now, the number of elements L of the Cartan subalgebra is known as the rank of the Lie group or the Lie algebra.
Tibra?
Yeah?
I'm not sure. The Maxwell's, is the Cartan subalgebra the spawn of the HI set?
Yeah.
Okay, so it's really the number of elements or the dimension of the set?
Okay, sure. Yeah.
So it's linearly independent.
Yeah, linearly independent. So you mean, okay. The dimension L of the CSA. Okay. So, wait. So if you have a representation on which the Lie algebra acts, so this is an important comment. The vectors of a representation that the Lie algebra acts will be then labeled by their eigenvalues of the Cartan subalgebra.
Excuse me?
Yeah?
Isn't that true only in a special case?
Right?
Because we have to have, oh wait, how's it called? It's a thing from quantum mechanics.
Yeah.
But it's not always, we can't always find a basis such that all of them, what's it called?
Are mutually diagonizable?
What's it called? Commuting set of compatible, no, something like that. Commuting set of compatible observables.
Yeah.
But it's not true that we can always, that this is always that, so to speak. So only if it is a CSCO, then we can label them by their eigenvalues, right?
I kind of don't follow.
Only if the eigenvalue is like
Real or something?
no. If I know, okay, so this means that when I know the eigenvalue, I know exactly which eigenvector it belongs to.
Right.
And that means that it's a commuting set of compatible observables.
Okay.
But the Cartan subalgebra doesn't have to be that.
Why not?
Well, because it doesn't. Because it's only in special cases it is.
I'm missing something here. I'm not really following the argument in detail. Can you explain it in more detail?
I don't know how to put it, except that I know that we have to be careful of that fact.
I mean, you may be right. Let's discuss this after class so we can, maybe you can illuminate me on the technicalities there.
No, I forgot some of the stuff myself, but that's the problem. But
well, it's okay. I mean, it's fine. Yeah. I mean, there might be something that that we can. That'll probably come up in the conversation. So yeah, let's go back to that. Okay, good. So now, consider the case when the n of SON is an odd number, right? So in that case, so I think this deserves its own blackboard. So consider n is 2l plus 1. So in that case, the extra dimension that we have can't really be paired with any other direction to give us a new plane of rotation that doesn't share an axis with those rotation, right? Because it's only one extra. So in that case, the rank is still L. So for every compact for every the algebra and here we are interested in Lie algebras mainly which arise from some compact group. So we can define the quadratic Casimir operator which commutes with all the elements of the algebra. So the Casimir is defined as it's a where we sum over all the elements of the Lie algebra. Now, I leave it as an exercise. Show it's a couple of lines that this thing so for SO3 the Casimir is given by the square of the three angular momentum operators.
Is that the general Casimir operator, or are you just saying it's for SON or something?
I believe that for compact Lie groups, that is the general Casimir operator. So I'm not giving you. So there are other Casimir operators. For example, for Lorentz group, for Poincare group, there are other nonlinear combinations, and there are even higher powers you can construct. but they hardly ever show up. And yeah,
Do you know why do you need a compact Lie group?
I'm not sure. Yeah,
Because Lorentz is not compact.
yeah, that's why I'm not defining this for Lorentz.
Regardless of that, but I guess I don't know. I don't know what the form is exactly. It's probably more complex for a general.
No, but that has something to do with why we cannot quantize gravity. Like we cannot construct like that easy passenger operator, right?
For parts, you can.
Possibly. I mean, no, we can construct. There's a what is it? The square of the Pauli-Lubansky spin vector, I think.
That's the Poincaré for Lorentz.
Yeah.
Just break it down into.
Oh, the Lorentz. Yeah, Lorentz is kind of like SO4. It's basically two copies of SU2, but there's funny signs and stuff like that, right? So yeah, I mean but I don't know what the connection with quantum gravity is. Yeah. I mean, different people tell you different things about why gravity can't be quantized, right? And there are people who claim, well, yeah, it can be quantized. It's just not, it is some kind of, well, they hope that it can be quantized, right? The asymptotic safety people.
Can I ask a question?
Yeah.
Usually, when we say rotations in SO3, for example, they usually don't commute. And here we said HI generate rotations in planes which do not share an axis.
Right.
What does the phrase here mean?
Okay, axis is not the correct word. Okay, that's a very good point. I should say direction. Yeah. That's a very good point. Thank you.
In SO3 they do.
Yeah. Share a direction, right? Because in 3D, we are used to think of rotation around axes, right? In higher dimensions, that's not the case. Rotations exist on planes, right? So basically, in 3D, the rotation is happening in this plane, right? So this is, say, I and J. Because of the Levi-Civita tensor, which maps, a plane to a direction orthogonal to it, right? That's why we can associate planes with axes, right? In higher dimensions, there's no such thing. So we have to, thanks for that, yeah. Okay. So there's a lemma, a very famous and highly used lemma in group theory called Schur's lemma. And Schur's lemma tells us that, say, any matrix which commutes with all the matrices of a representation of an irreducible representation must be proportional to the identity. So if TR are the, say, generators in the irreducible representation R, then this is up to some number which depends on the representation. This is R, must be the same as this. So this number often characterizes the whole irreducible representation. So for SO3 or SU2, you know from quantum mechanics, C2 is the total angular momentum squared, eigenvalue of the total angular momentum squared operator, right? So let me quickly move on to a generalization of the SON groups, which is useful in physics. Yeah.
Is that statement TA times TA supposed to be an obvious result of Scher's lemma? It's the same as.
Yeah, because it commutes with all the matrices of a representation, so it must be proportional to that. Yeah. Sometimes obvious things are not obvious. Okay, so so these are very useful groups, and there are a couple of application of these groups in physics. Okay, so we can think of the SON groups as preserving the Euclidean metric. So O transpose the Euclidean metric, which I write as identity matrix, O is this. So for analogously, for spaces such as R and M, which have like a flat metric given by a diagonal matrix where we have, say, n minus signs and, say, m plus signs, so the ON comma M group is defined as all those matrices which leave this metric. Sorry, yeah. So this is all those O which which leave this metric invariant, right? And if we impose the further restriction that the determinant of O be 1, then we get the subgroup n comma m, and this is the subgroup that is continuously connected to the identity. So the most famous example of this family is, of course, the Lorentz group. Okay, before we go there, let's just make a comment that as group manifolds, these are non-compact manifolds. So we call them non-compact groups. I'm just going to make a statement that is, I'm not going to even attempt to prove, but it will become very important when you do quantum field theory. And the statement is, there are no finite dimensional unitary representation of non-compact Lie groups. And this fact will rear its head when you go and quantize fields in your KFT1 course. Okay, so the most famous example is the Lorentz group. Technically, the Lorentz group is O1, 3. And the subgroup that what we call the rotations and the Lorentz boosts, there are subgroup. The subgroup that is continuously connected to the identity, and that's called so that's SO1, 3 is a subgroup. And I think it's called proper orthochronous Lorentz transformations. And what it does is that proper means that, okay. So proper means that, so the determinant is 1, and which means that it's continuously connected to the identity. But we also impose a condition, it's orthochronous, which means that the 0,0 component of the matrices of the group is actually it's positive. No, it's negative. Sorry. Yeah. Or
No, it's positive.
it's positive. Sorry. Yeah. Sorry, I don't think it's dependent on the metric. So what it means is that it cannot change the direction of time. Yeah?
On that statement, the claim you made, are there other restrictions? Because, for example,
Sorry, can you speak out a bit louder?
on the claim you made about non-compact
Right.
are there other restrictions? Because, for example, you can always construct the trivial representation.
Okay, yeah, that's
So
yeah, okay, that's good. No finite dimensional, unitary,
Irreducible, maybe.
irreducible, right?
That's I think controversial.
Sorry?
Ah, yeah.
Sorry, some? Yeah, I think it's, yeah, I think that's, okay, yeah. So what we'll see is that the particles in quantum fields, that's actually an infinite dimensional Hilbert space. And of course, the particles, the bracket of particle states must be, in the norm of the particle state must be positive, right? So it has to be unitary, otherwise quantum mechanics wouldn't make sense. But the fact that they're representation of the Lorentz group means that, that's connected to the fact that representation is infinite dimensional, that the Fock space can have as many particles as you want. Okay, coming back. So if I draw some sort of space-time diagram, then we have like the Lorentz group. What they do is that it takes some future pointing time-like vector to other future pointing time-like vectors, and it does the same thing for, say, backward pointing or pointing time-like vectors to other time-like vectors, but it cannot switch this guy to that guy. And so this is inside the light cone, and the space-like vectors, as you know, there is no notion that they're either future directed or past directed. So the space-like vectors, the Lorentz, the proper orthochronous Lorentz group will take them along this hyperboloid. So the O13 group contains elements such as parity, which inverts all the direction of space-time. This is known as parity. Now, up to a rotation, parity is reflection. So if you have a mirror, I mean, the mirror doesn't, of course, invert all these directions, right? So it only inverts one of these directions. But you can show that up to rotation, parity is reflection. And the other thing is time inversion. So if you run the physics that you see if you run the clock backwards, so time inversion. So these are elements of the Lorentz group, which is not part of the SO 1,3. So another application of the SON, M groups are the symmetry group of ADS spaces. So what is an ADS space? It is the evil twin of de Sitter space. Actually, de Sitter space turns out to be the evil twin of anti-de Sitter space. And it's like a movie where you think, this is the good guy, but on the end, there's like a twist, right? But we seem to be living in a bad movie because we seem to be living in some kind of de Sitter space, or at least something that'll asymptote to one eventually. All right, so the symmetry group, or isometry, as geometrists like to call it, isometry group of ADS-N. So ADS-N is defined by a hyperboloid in a Minkowski type of space with 2 time direction. So by this equation, so these are the coordinates of this guy, and this is equal to, and this is the radius of ADS. So this formula is invariant under SO to n-1 and also O to n-1. But because we are thinking of it as symmetry, we are restricting it to the SO, SO to n-1. It turns out that there's certain field theories called conformal field theories. So a conformal field theory in n-1 dimensional space-time, dimensional flat space-time, has the same symmetry. When you go to quantum field theory, you'll see that if you have a number of quantum field theories, you can do rotation in field space. And it turns out that if you're looking at a conformal field theory in n-1 dimension of flat space, it has the same symmetry as the isometry group of ADS-N. And this was an important clue in the ADS-CFT conjecture, which since then has become a theorem without proof. So that these, because a lot of things, symmetries on the 2 sides have to match.
But to do that, do you compute the commutators or something in the Lie algebra of this ADS-N and see that they satisfy the Virasoro algebra or something?
Okay, so that's a very good point because I glossed over something, and the idea is that when the conformal let's call it CFT, conformal field theory, is in 2D. So it's on 2D space-time. It turns out that you can, under certain circumstances, the symmetry group becomes infinite dimensional. And there's a subgroup of this infinite dimensional group. So, okay, so this infinite dimensional group, the Lie algebra, is the Virasoro algebra. And there's a subgroup of this Virasoro algebra, which is this guy. Okay? And I think in that case, it's given by SL2R. That is the the isometry group of SL2R is SE2, yeah, of ADS3. But in 2 dimension, something interesting happens because you can map the 2-dimensional plane through some weak rotation. You can map it to the complex plane, and as we know, all the conformal transformation on the complex plane, they preserve angles, and yeah. So okay, so maybe we can take a 5-minute break. Or yeah.
SONM the same as SOMN?
Is SONM the same as SOMN? No. If it were, then we would say SO1, 3 is the same as SO3, 1. SO3, 1 would be in a space where we have 3 time dimensions and 1 space dimension, where SO1, 3 would be a Lorentz group in a space which has 1 time dimension in 3 space dimension. So the 2 time dimension here is just like, this doesn't have any physical meaning, because the hyperboloid that we're defining, the intrinsic metric on this hyperboloid has only 1 time dimension, right? Because this eliminates actually one of the time-like directions. Shall we take a break for 5 minutes? And I'm here if you want ask more questions. All right. So the last example of the SON groups has to do with parallel transport. So what is that? And this will be very sketchy. So the last example is application to holonomy groups. So suppose you have some manifold, and for definiteness, let's take a not so nice sphere. Well, imagine it's a good sphere. And so as you know that on a curved manifold, we can't really, vectors are not globally defined. They have to be, you have to be careful when you compare vector in 2 different places. So there's a notion of parallel propagation, and on a manifold, there can be many different ways, prescriptions for propagating a vector, in a way that you call parallel. So, for example, suppose we take a great circle, and we take a vector that is tangent to the great circle at the equator, and then we, propagate it to the North Pole, always keeping it tangent to keeping the angle the same with the great circle. And then suppose we now bring it back again, keeping the angle the same all along the great curve, and then we bring it, as we reach the equator, we bring it back to the original point again, keeping the angle between this guy and the curve that I'm moving it along to be the same. So as a result, we see that as a result of this parallel propagation, we see that the original vector has rotated by some angle, right? In this case, it's probably 90 degrees. So if you were to consider some general manifold and some generic closed curve and parallel propagate this vector, some vector around the closed loop, in general it'll come up to the original vector. So this is the parallel propagated vector. It'll come back to the original vector up to some rotation, right? If we make the constraint that so if we we say that the length of v doesn't change, then it must be that this v and this v prime is just rotated from each other. So now you can actually give this a group structure, and this will be very sketchy. I'm sorry, it's very interesting, but if I go deep into it, it'll just take up a lot of time unnecessarily. But so the way you do it is that, okay, you start with a point and you say, okay, I associate with every closed loop some element of SON. So this is, say, lambda 1. And so there's another closed loop which rotates the vector up to some other rotation, lambda 2. Okay? And then the group multiplication consists of taking a vector and and first rotating it, like parallelly transporting around the loop 1, and then parallelly transporting around the loop 2. Okay? So that's a group multiplication. And the group inverse is just if you parallelly propagate the vector in one sense, that's lambda 1. But if you parallelly propagate that vector in the opposite sense, so if you go this way, that will give you the inverse of that group, so on and so forth. And so this is known as the restricted holonomic group. And then it depends on the point you've chosen, but if the manifold is connected and compact, you can actually extend this group structure to all the closed loops around which you can parallelly propagate.
I have a question.
Yeah.
How are you assigning a SON element to a loop?
Right. Okay. So what you do is that you say that I start with some small vector here. And it could be it can be looking at any direction, and you have to tell me that there is some notion in which this vector can be parallelly propagated. So for example, what we call the Levi-Civita connection or the Christoffel symbols in GR, that is a prescription for doing just this, for parallelly propagating a small vector. And so suppose I take the Levi-Civita connection for definiteness, right? So then I can integrate that equation, and then we can come back and we will find that, this becomes V prime. So because the Levi-Civita connection, or any connection that we're considering, is metric compatible, that means that the vector that we parallel propagate, its length doesn't change. So it must be that this vector and this vector are in the same tangent space, so they must be rotated by SON. So that's how I associate that, and you can show that this rotation is independent of which vector you took from the initial tangent space, right? And that's how we assign like a group element to a loop, to a.
But is this loop unique? I mean, you can have a different loop with the same lambda.
Okay. That's a very good question. I don't think it is. No, it's not. And I think I think you probably have to have some equivalence class relationship there then. Yeah. So, yeah.
So with this procedure, are you assigning the group to each point on your manifold?
With the restricted holonomic group, yes. Yeah.
So if I remember correctly from my topology class,
yeah.
Basically you take the equivalence relation of loops being homeomorphic to one another.
Right.
And then you split the manifold along this relation. I don't know English word for it. And then you do the group structure on these classes.
Right. Okay.
Somebody else.
Right. Yeah. Yeah. You might quotient it, right?
Yeah, but that was a long time ago.
No, but that's exactly, that's basically what I'm saying, is that you can have an equivalence. So, yeah, I mean, but for that to happen, you have to have some kind of a connected.
It's only important that within those classes, these curves are continuously
deformable.
Yeah. One into another.
Right. So the technical, assumption would be that they're connected and simply connected, right? Meaning that a manifold is simply connected. If every closed loop can be deformed continuously to a point. So we will see that the manifold for SO3 is not simply connected. I will ask you to show that in today's tutorial. It is easy-ish. Okay, so this is just like I just wanted to know the kind of the term of holonomic group. It crops up sometimes in various different guises. The next on our list is the special unitary group, and I really want to get to this. This is very important in particle physics and quantum mechanics. So the special unitary groups SUN. So it turns out the gauge symmetry group of the standard model is given by and there's some Z2 factor here that I don't remember correct. I say symmetry because it is debatable that the gauge part of that symmetry is actually a symmetry group. The standard model also has some accidental U1 symmetries. So it has some accidental global U1 symmetries. What I mean by accidental is that once you have fixed your Lagrangian to respect that symmetry, those symmetries come for free. And such as like the baryon number and lepton number conservations. Those are the examples of the accidental symmetries. Okay, so what is an SUN group? So these are parenthetical remarks. So SUN, okay, let me be consistent, consists of n by n complex matrices which satisfy complex matrices, say U, which satisfy that the Hermitian conjugate of U is the same as the inverse. You can also write this as U dagger U is U dagger 1. And the determinant of U is +1. If we didn't impose this condition, we get the UN group. Nothing to do with the United Nations. Okay, what is the dimension of this group? So U, as a complex matrix, has in principle 2n squared real parameters. But not all of them are going to be independent. So if I look at these conditions now, say I look at them in components, then it becomes where there is a sum over J. Now if I set I is equals to K, then we get n real constraint equation. If I is not equal to Z, K, then the upper triangular part is related to the lower triangular part of this condition by complex conjugation. So we only need to, consider, say, I greater than j. Then we get, how many components are there? There are n times n minus 1 complex entries, so by 2. And so if I count the real number of parameters, it'll be 2 times of that. So that means that if I now subtract these guys, we get n squared parameters. So the additional determinant of u equals to 1 eliminates. This is one real equation you can verify. Eliminates the 1 extra parameter. So we find that the dimension of SUN is then n squared minus 1. So let me make a comment about its relationship with UN. So the determinant of u equals to 1 eliminates matrices, diagonal matrices of this form, up to a caveat. So see that these guys, they form a U1 subgroup because they're diagonal, and they basically commute with all the others. It does not eliminate discrete. So this is an example of a abelian. It's a normal subgroup, right? We can still have discrete groups, right? So for example, if we have, so if I take the determinant of this guy, so the determinant of this guy is going to be I theta n, right? Now so this is, for generic values of theta, this is some phase, so this is not equals to 1. But if I say theta is going to be, say, 2 pi k over n, where k is some integer, then the determinant of u is is 1, right? So that means that this condition eliminates the U1 subgroup, but it doesn't eliminate the cyclic groups, say CK. So we can still have, for example, e to the power I, say pi by 3 sorry, e to the I 2 pi I by 3 k so this will generate, I think, C3, right?
it eliminates the U1 subgroup from what?
So if you had not, imposed that condition, we would have UN, and UN has U1 as a subgroup. So and when we impose this condition, it eliminates the U1 subgroup of UN, and that remaining subgroup, we call it SUN. Okay. So what are the generators of SUN? If I write U as in this way, where these are real n squared minus 1 parameters, then U dagger is U inverse. That tells me that these matrices have to be Hermitian. So the determinant, and this just, if you just expand this as a power series, then you can right, yeah, and you can verify this, and then if you have the determinant of U equals to 1, so the determinant of U turns out to, you can show, is equal to the trace of the argument of the exponential. So this is equal to 1 means that the trace of the argument of the exponential has to vanish, since the trace is linear, and the zeta a's are arbitrary parameters. This means that the generators have to be traceless. So the generators of SUN group have to be Hermitian and traceless. You are familiar with this in the context of SU2.
Sorry.
Yeah.
When you say condition that TA dagger is equal to T upper A, is
Oh, sorry. It should be lower. Yeah.
okay. I was wondering if there was some significance to you.
No. Yeah, it's just me being sloppy.
Could there possibly be a sign in there as well?
You mean minus? No, but let's see that. We can see that. Let's see. Okay, so let's take U, and U is e to the power I this thing, right? And so I can write this as a power series. Right? Now, I say that, okay, U dagger is like that, then what I will have is I will have, say, one, all the i's are going to be, become, they're going to become negative I, right? These guys are the same, and then this will become this, right? And right, so in other words, I can say that this is going to be e to the power minus I, this thing, TA dagger, right? And now, sorry?
This has to be the inverse.
Right, so now you can play this game and say, okay, what happens if I now compute this? And I'm just thinking if I should use. Right. Yeah. Sure. Yeah.
I think we should start with
Right. Okay. So. Right. So it's only if to show it actually rigorously, I think you have to use the BCH formula, where but you can see that if you say that, okay, if I just say that TA is Hermitian, right, then this will become, these two, in that case, these two matrices, it's easy to see they are essentially the same matrix up to a minus sign. Therefore, you can write this as right. So does that convince you, or okay? But okay, or you can just, if you want to see in more details, you can actually use the BCH formula and some properties of TA. Okay, so an example of this group is SU2, and in that case, the generators are given by half of the Pauli matrices, and you know that they're Hermitian and they're traceless. Okay, I'll probably go about 10 more minutes, if that's all right. So what are the generators? What do they look like? So these are n by n matrices, and all the generators have to be Hermitian and traceless. So you can have H1. So we can choose n minus 1 linearly independent diagonal matrices of this form. So I'm just keeping the last one minus 1 and changing the other diagonal. So right. So there should be, so these are n minus 1 matrices. The rest of the matrices, there are there are n minus 1 remaining. Is it n squared minus 1 minus n? So here we have, so n minus 1 plus n squared minus. Yeah, okay, good. Yeah, so it counts, it adds up. So there's, of these, you can choose half of them to be real and symmetric and non-diagonal. The other half, you can choose them to be pure, the other half to be pure imaginary and antisymmetric. I leave it as an exercise for you to work out what the other generators are. But the point here is we have the n minus 1 mutually commuting generators. So that means that the rank of SUN is n minus 1. Yeah, that's an important result. So let me finish by giving a couple of definitions and proving a result, well, showing, like addressing a question that was raised in last lecture about the irreducibility of the adjoint representation. That is, under what condition is the adjoint representation irreducible? So let's start with introducing a concept of the simple Lie group. So a simple Lie group is a connected non-abelian Lie group which does not have a non-trivial, probably connected normal subgroup. Most of the groups we'll come across are going to be simple. However, there'll be some important exceptions. The Lorentz group turns out to be one of those exceptions. Although, sorry, we are talking about if you talk about compactly groups, then SO4 would be an example which is not simply connected. We'll see that. Okay. So there's an important note. The excluded normal subgroups are Lie groups themselves. So for example, in other words, a simple Lie group may have discrete normal subgroups. So that's why we defined a simple group before for the discrete case, but that's why we have to define the simple Lie group separately, because you can have a normal subgroup of a simple Lie group as long as it's a discrete normal subgroup. So for example, we saw that you can have like these, cyclic groups. Yeah?
Sorry, is this like we exclude them from the definition, or this cannot happen mathematically?
We exclude them from the definition.
Okay. Okay.
Yeah. That's a good point. Yeah.
Is the connected part in the definition defined as in homotopy? It's
Yes.
connected in the
Yeah.
sense
Yeah. So it doesn't break up into two different manifolds. Yes. And you will see that, for example, SO4 is not connected.
And just connected, not simply connected.
No, there is no restriction on simply connectedness. In fact, SO3 we will see is not simply connected. Okay, so related notions is a simple Lie algebra. Suppose we have a Lie algebra, which say I denote by G tilde. And so K is some subalgebra now K is said to be invariant. K is invariant if the commutator of K with all the elements of G, of the Lie algebra G, is either in K or vanishes. So this is called the K is invariant, or K is an invariant subalgebra. So if a Lie algebra is simple, okay, sorry. We say that a Lie algebra is simple if it excludes, okay, if it has no invariant subalgebras. So it has no non-trivial is okay. Sorry, non-trivial invariant subalgebra. Yeah. So a simple Lie group gives rise to a simple Lie algebra and vice versa.
Just a question.
Yeah.
When we define the invariant subalgebra, is it the commutator equals to K, or does it belong to?
Yeah.
Can it be a subset?
Yeah. So it's yeah, something like this, right? But
Then we don't need the zero part, actually. It wouldn't be a subalgebra if it didn't include zero.
right, yeah. Technically, you don't need the zero because it's already included. Okay. So a simple Lie group gives rise to a simple Lie algebra and vice versa. So I just want to show something. Suppose the Lie algebra, this is simple. But the adjoint representation is, say, reducible. So I'm going to assume that what it means that we can take the adjoint representation and write it in some basis in which it is block diagonal, right? So if I write this in terms of equation, so what I do is that, okay, the indices in this block, I'm going to label them with A tilde, B tilde, and this block A bar, B bar, and over here it's A tilde, say B bar, and similarly here. So I can say that f of A, the element BC, is if they are so they're non-zero if both of these the BC elements have barred indices, or if they have tilde indices, because then they belong either elements are in this block or this block. Whereas if they are not in that block, then they are zero. Now, according to the definition of the adjoint representation, this is minus I F A B bar C bar. But we can use the antisymmetry to write this as plus I F B bar A C bar. But this is nothing but F B bar A of C bar. Now this is 0 if A is not a barred index. Right. So now, if I set, this means that if A tilde B bar of C bar is 0. Using a similar logic, I can show that F of A bar B tilde C tilde is 0. Since the set of generators consists of FA tildes and FA bars, and we have established that FA bar, the tilde elements of these guys are 0, and the FA tilde, the barred elements are 0. In other words, let me just use this. In other words, we have FA bar has the form of and FA tilde then it follows that these are all they are invariant subalgebras, right? So if they're invariant subalgebras, that means that that the group is simple. So and therefore it cannot be true that our assumption that it forms a reducible representation. So that is my that's how I think it should go. But what is important here is the assumption that
simple or is not simple. Here implied.
Well, if we
This is
simple.
This is not simple.
Yeah. So yeah, is not simple. So we have a contradiction, right?
Yeah.
Yeah. Okay, I think I should stop here. Sorry for taking so much time. But some of the other questions I will address in the next lecture.